many people have asked me to. All right, so pull out the worksheet. It's so F's in the chat if you manage to get the worksheet up. Great, great. So the major topics on the worksheet for today are dot products, cross products, and planes. So equations that define planes in 3 space. Let's start with the dot product section. I think that the first one, part A, is a good warm-up. So let's do that. And F's in the chat when you've managed to figure it out. Out of curiosity, do you guys actually have to turn in the worksheets? Someone asked me where you turn the worksheets in. I don't think you have to turn them in. Yeah, so don't worry about that. Okay, great. So we're starting to get some F's here. I'm happy to see that. So I have 6 F's out of 13 people who are in my section. What happened to the others? Oh, okay. So if you're confused, that's a good question. I always ask for F's if you're able to solve the problem, but I don't ask for anything if you're not able to solve it. So I guess maybe if you think it's embarrassing to put something in the chat if you don't understand, which you shouldn't be embarrassed, because being confused is a natural part of learning. But if you're not embarrassed, just write "I'm confused" in the chat or something, or you can directly message me. Yeah, maybe I should come up with like a different letter that you can send me if you're embarrassed or confused. Maybe like a C for confused. Okay, so let's go over it. The main point here is just to get some practice with the law of cosines, right? Because you have VW is equal to VW cosine theta, okay? And so all we have to do is we need to make sure that this side is equal to minus VW, okay? And all this entails is ensuring that cosine theta is equal to -1, right? And so the place on the unit circle where that happens is precisely at pi, or 180 degrees. It doesn't matter. Okay, so that's how you do the first problem. And I guess geometrically, intuitively, what is this saying? Well, the dot product is giving you sort of the extent to which one vector lies along another vector. To what extent does its magnitude pass along the direction of another vector, right? I mean, it's sort of rough, but what we're saying, if we have v dot w equal to exactly the negative of the magnitude v times w, is we're saying that the components of these vectors lie directly opposite to each other, okay? All right, so let's try problem 2, and or problem B, and let's do I and II, okay? Oops. Oh, the audio lag. So we're going to be doing problem 1 in dot products, B parts I and double I, okay? So F's in the chat if you get it, and then you can put C's in the chat if you're confused, or just DM me a C. And there's no punishment and no shame. And also, if you're confused and you don't know how to proceed, then one good thing you can do is, if you send me a C, you could also tell me either what you tried, or you can explain where your confusion is if we're still waiting for other people, but you don't have to. All right, so I have no F's and I have 2 C's. Okay, 3 C's for part 2, 4 C's, 5 C's, excellent. How about the other 7 of you? Or All right, so it looks like everyone's confused about part 2. That's perfectly okay. So the idea here is let's start with v dot w, okay? So for v dot w, we can use the law of cosines, right? So v times w cosine theta. We have all of these quantities. They're 3, what did I make them? 3 and 2 and cosine 120, right? So maybe it'll take me, so I think cosine of 120 is minus 1/2. And so that gives you minus 3. So hopefully people are happy with that for part 1, right? So let's try part 2. Part 2 is a little bit trickier. The idea here is that, again, we have no information directly about what the individual components of v and w are. So we're going to have to do something a little bit more creative. And what we'll have to do is, although we can't compute the magnitude of 3v plus 2w directly, what we can do is we can compute its square using linearity of the dot product. So we can rewrite this magnitude squared as 3v plus 2w dotted with 3v plus 2w. And remember, these angular brackets are just another way to write the dot product. And so that gives you, using linearity, meaning you can expand this thing, 9v squared, matching these two terms, plus, so we get a 6 here and another 6 here. So that gives you 12 v dot w. I prefer this notation. Plus, and then we just take the product of these two and we get 4 w w. And the 4 again comes from the fact that we have a 2 here and a 2 here that we just pull out, right? So that gives you 9. What was v again? 3, right? So 9 times 9 plus 12, and we know what v dot w is from the previous part. It's just minus 3 times minus 3, plus 4 w squared. And what's w squared? It should just be 4. And so that gives you 81 minus 36 plus 16. And that gives you 81 minus 20, which is 61. Then we take a square root on both sides and we get 3v plus 2w is equal to root 61, okay? And I'll spare you the details of part 3 because it's basically the same. So are people happy with that?
I have a quick question.
Yeah, go for it.
The angular things, like I thought that described vectors, not like you said it described dot. What you said something described dot.
So
Okay, yeah.
there are different notational systems that people use. In this class, you're generally going to denote a vector like this, okay? I'll get to the other question in a sec. So this is how, in this class, we'll denote our vectors like this, and the dot product usually like this, okay? But sometimes I deviate from the notation. It's not intentional, it's just that there are different ways to write these things. So the way that I learned it was you denote a vector like this, and you denote a dot product like this. So if I accidentally use this notation, just roll with it, okay? Yeah, but for this class, you'll usually use the first one, and I'll try and stick to it. Sometimes I just forget. Okay, why did I square it? I squared it because I had information that allowed me to compute the square of this magnitude, whereas I didn't have any information that would allow me to compute the magnitude directly, okay? Because if you square it, anytime you square something, square a magnitude, you're able to rewrite it in terms of a dot product. And we had information about that. Whereas if I just tried to bash directly at the magnitude, I have no tools to do that. So that's the thought process. And it's a pretty common technique, actually. All right, let's go on. The third part of this question is purely conceptual. So I just want to explain it because I think it's interesting. So the question is, if you have some vector in 3 space, what is the space that when you dot it with ABC, you get 0? Okay, so V dot ABC gives you 0. And the answer is, in 3 space, it's a plane, okay? So what's the relation between the dimension of a plane and the dimension of 3 space, right? So they differ in dimensions by 1. And how we can write this set here, that's the solution set V dot ABC equals 0, is AX plus BY plus CZ is equal to 0. Okay, so all X, Y, and Z. And basically you can connect this to linear algebra in that you have some sort of equation that is giving you a 0 set, and the number of these equations reduce the dimension by 1 each time, right? Like if you have 3 linear equations and 3 variables, you're certainly able to find a solution, right? As long as they don't like directly contradict each other or something. No, as long as you're always able to find a solution. And let me explain why. Basically, because if you have one of these vectors, the area that's dotted with it to get 0 gives you this set. And then if you add a second one, you get basically another plane. And so the intersection of 2 planes gives you a line. And then the intersection of 3 planes, as long as they're linearly independent, as long as one of the planes isn't the same as the other 2 or just a rotation of it. So the third plane, when you intersect all 3, will give you a point, okay? And those correspond to when you have 3 equations and 3 different variables, you can always find one solution. So each equation reduces the dimension of the space by 1. And this holds in higher dimensions too. Like if you have an n-dimensional vector, then the space such that the dot product with that vector gives you 0 is going to be n-1 dimensional. And then if you add a second linearly independent equation and you dot with that too, and require that it's 0, then you get an n-2 dimensional space, okay? So the point here is just that you can define surfaces called hyperplanes in n-dimensional space using the same technique of the dot product, okay? Okay, so let's go on to cross products. We'll start with part A, because if you can't do the computations, you'll certainly be lost on the rest of it. So let's go over those. And F's or C's in the chat. Yeah, so let's do pure computations, part I and part II. No, so part A, parts I and II. My apologies. C for part 2. Okay. Right, so it seems like people are confused about opposite things. How about other people? All right, so it seems like most people are confused about part 2. All right, let me start going over it. So any final feedback? Are other people confused or having some luck? Okay, so another C. Great, okay. And I guess this shows you that if you were silently confused before, it seems like most of the class is often confused. So don't worry about it. All right, so for the first part, remember that if you take the cross product, you learned in class that the magnitude of the resulting vector is equal to the area of the parallelogram, right? That's spanned by these two vectors. And what we need to do in order to get a zero cross product is just ensure that this parallelogram has zero area. And what does this mean? So if we take the first vector over here, then we have two choices. We can either take the second vector in the same direction as the first, and then the parallelogram that completes this thing looks something like this, right? Yeah, so you're just multiplying the vector by itself. And you could also choose this vector because the resulting parallelogram also has zero area. It just turns out to be a line. And so any scalar multiple of the first vector will do. All right. Now for the second question, hopefully everyone knows how to find one vector that's orthogonal to these two, right? So can I have an F in the chat if you know how to find one vector that's orthogonal to those two? Great, okay, so generally speaking, if you know how to find one vector that's orthogonal, you know how to find infinitely many. Why? Because orthogonality is determined by direction, not magnitude. And so you can rescale the magnitude of the vector you found however you want, and you'll still get another orthogonal vector. Okay, so if we take 1, 3, 5, and what was the second one? 1, 8, 9, and we take the cross product, then we get 27 minus 40 I hat minus j hat times 9 minus 5 plus k hat times 8 minus 3. And that gives you minus 13 I hat minus 4 j hat plus 5 k hat. Does everyone agree with that? Great. So now just rescale it however you want. You just multiply by some lambda and you're good to go, okay? 40 was from 8 times 5 in this minor determinant. Great. Let's go on. I think we can skip part 3 of A, and we can also skip, yeah, so that's what I originally intended you to do when I wrote the problem, which just flip these two, and by the right-hand rule, you'll get the vector that's opposite. Okay. So let's skip part 3 of A because it's another computation. Let's skip B and C because we did B last time and C is pretty similar to B. So you can think about those in the privacy of your own home if you feel like it. And let's go on to D. So U dot V cross W equals 0. What does this tell you about U, V, and W? So this is kind of a conceptual question. Would anyone be willing to say what they think if they think anything?
This is just a guess, but oh wait, I was gonna say V and W were orthogonal, but I think that's wrong. Never mind. That's wrong.
So it doesn't tell you that V and W are orthogonal, but that's a good guess. Yeah, so it tells you that U is orthogonal to V times W. So that's great. That's a good start. And what can you deduce from that? Olivia is actually very close. They're not quite parallel, but can you say something else? Okay, let me help you out. So let's draw a picture. If we have V here and W here, then their cross product is up here, okay? So this is V times W. And so what does it mean if U is orthogonal to those two? That means that U lies somewhere in this plane. Come on, draw. This plane that is spanned by V and W, okay? And so what this says is that U, V, and W all lie, they don't form a parallelepiped because in order to form a parallelepiped, they have to not lie in the same plane, okay? So specifically, in this case, all three of these, they have to lie in the same plane, okay? And this is by no means given. Like consider the box. This is like a pyramid. These three vectors don't lie in the same plane because they define some sort of three-dimensional shape. But if we just take these three vectors that lie, that touch the edge of a circle, then they do lie in the same plane, okay? So that's what this is telling you. Okay. And interestingly, I guess one side note, is this is the same as doing the computation U1, U2, U3, V1, V2, V3, and W1, W2, W3, and taking the determinant. And remember, this computation gives you the area of the parallelepiped, or the volume of the parallelepiped that's spanned by U, V, and W. So if that's 0, it means that it has to be completely flat, and then the volume 0. All right, so the next section is the hardest, but I think it's good. Let's do 3A parts. Well, let's try part 1. And if you get part 1, do part 2. But they're very similar. If you get 1, you can get 2. Is this part from yesterday's lecture? Well, I actually don't go to lectures except the ones on Friday. So maybe someone else can answer that question. I saw it on your syllabus though. Okay, so do we have any ideas for this problem? This one, if you understand planes, it should be immediate. Okay, so are people confused? Okay, so people are confused. Let me say something about planes. So if you have a plane, basically a plane is 2 pieces of data. It's a normal vector. We talked earlier about how a normal vector dotted with like everything. So say this is V. Everything that you dot with V, so all vectors say X dot V, such that this is equal to 0. So the X that make this 0, these give you the vectors of this plane, okay? And there's a second piece of data that you need, because if all you have is a normal vector, I can shift this up and down. I can move it down here, and I can move it up, and it just by shifting along this normal vector, and you'll get another vector with the same, another plane with the same normal vector. And so you need some other piece of information. And that second piece of information is a point that lies on the plane. It can be any point on the plane, and these 2 pieces of information define a plane, okay? And in this case, what we have to do is, the way we find the normal vector is, if our plane is defined as 2x plus 3y plus z is equal to 3, the normal vector is going to be 2, so these coefficients, 3 and 1, so 2, 3, 1, okay? And so that means that our plane has some sort of equation that looks like 2x plus 3y plus z is equal to k, where k is a constant. And now all we have to do is find k. We know that this plane passes through the origin. And so if we plug in 0, 0, 0 for x, y, and z, we get 0 plus 0 plus 0 is equal to k. So k is 0. And that gives you that the equation for the plane is 2x plus 3y plus z is equal to 0. So now, can someone tell me how to do the second part? So I'm starting to run down my clock. So maybe I'll just say something, which is, so it's the same process, okay? You have your normal vector, which is again just 2, 3, 1, but now we have a different point on it. So if we have 2x plus 3y plus z is equal to k, and we plug in the point 5, 6, 7, we get 2 times 5 plus 3 times 6 plus 7 is equal to k. And that's just 10 plus 18 plus 7, which is 35. 10 plus 18, 28, and 7 is 35. So that gives you 2x plus 3y plus z is equal to 35 as your equation. Okay? So, right, I'm actually very low on time, so I'm not going, yeah, I guess I'll just explain a couple more of these if that's okay. 3, 6, and 7, that was the point that I gave you that lies on the plane, okay? Yeah, so let me talk for a second about part B. So here it asks, what is the equation of a plane that contains 3, 4, 5, and 2, 4, 1, right? So if we have these two vectors, which are 3, 4, 5, and 2, 4, 1, not drawn to scale, then all we need in order to get a plane is we have to have some normal vector to these two. And luckily you have a process for finding the normal vector. That is the cross product. So if we cross 3, 4, 5 with 2, 4, 1, then we end up getting I hat times 4 minus 20 plus j hat times 3 minus 10 plus k hat times 12 minus 8, okay? And that gives you minus 16 I hat plus, minus 7. Wait, I dropped a minus sign, I'm sorry. So it should be minus j, right? So plus 7 j hat plus 4 k hat, okay? And so now all we have to do is make sure that it's the right plane, because of course you have infinitely many just by shifting. And the way that you ensure that it's the right plane is you just make sure it contains one of these points, okay? Because you know that vectors and points, they're kind of the same here. And so if you plug in minus 16x plus 7y plus 4z is equal to k, and we just plug in 2, 4, 1 or 3, 4, 5, doesn't matter, they'll define the same plane, then you'll be able to solve for k, okay? And I'm not going to do that computation right now. So the orthogonal vector is just orthogonal to the plane, the normal vector. Yeah, that's right, that's right. What do you plug in? You either plug in the values of this point or the values of this point, okay? Great. So I want to go over very quickly. I'm probably going to go over overtime a little bit, but if you have to leave, that's okay. But I think C and D are great questions. Of course I do, because I wrote them. but if you have a chance, I think you should definitely try them out in the privacy of your own home. But let me talk about C for a second. C, so the question is, if you have two planes in space, you want to know, so they're your planes, I guess dotted lines are better. If you have two planes that intersect in space, you want to find the equation for the line that defines their intersection, okay? And what does this mean geometrically? Well, you know that the normal vector to this plane looks something like this, and the normal vector to this plane looks something like this, right? And so if we think about the normal vectors over here, we have one that maybe points like that, and another one that points maybe out of the page like this. I'm sorry, it's very hard to draw. But if we take the cross product of those two, we should get a line that runs along the intersection, like a vector that lies in the intersection of these two planes. Okay, does that make sense, or are people lost? It makes sense. Or wait, it makes sense or you're lost? Great, okay. So what we do here is we take so the equations for our planes were x plus y plus z plus 1 and x plus 2y plus 3z plus 4, okay? And so the normal vector is again just 1, 1, 1 for the first one, and 1, 2, 3 for the second one. So let's compute the cross product. So compute that, you get 3 minus 2 I hat minus j hat, 3 minus 1 plus k hat, 2 minus 1, and that gives you I hat minus 2j hat plus k hat, okay? And so now you need one more piece of information, right? So this is the vector that is parallel to the intersection of these two planes, right? We don't know where it lies. Like it could lie up here, it could lie up here. Right now, we've just written it so that it's at the origin, right? But in order to write a parametric equation for the line that's the intersection of these planes, what we're going to have to do is we're going to have to take this line, which we can rewrite as 1 minus 2, 1, and multiply it by t, right? So this is a parametric equation. So if these are our axes, that gives us this vector, except pointing from the origin. Again, not defined, not drawn to scale. So it should be sort of like that. Okay, so now what we have to do is we have to translate it up here so that it's in the correct location to pass through the intersection, okay? And all we have to do in order to do that is we have to find a point in the intersection to shift it by, okay? So a vector or a point that lies on the intersection of the planes so that we can shift. And how do we do that? Well, there are infinitely many choices. So we're going to have to just solve these two equations and find some point that satisfies both of them, okay? The way that we do that is, well, we can eliminate x. So we get minus y minus 2z, and then minus 3 is equal to 0. Okay, so that's one equation that satisfies both of them just by subtracting. And then you get so y minus 2z is equal to 3. And that's one equation. And now we just have to find an x that's going to satisfy both of these, okay? So how do we do that? We really just need any point, right? It doesn't matter which point it is as long as it's on this line. And so maybe, yeah, wait a sec. We have to, Yeah, we have to find a point that's in the intersection. So we just need a solution to these two equations. I'm just thinking about what's the best way to get this. Well, maybe what we want to do is we want to fix y and then find equations for the other two that satisfy it. Okay. Oh, sorry. So I have a question. If we are having trouble computing the cross product, could we go to office hours to go over it? Yes, of course. So it's 7 p.m. on Thursdays, okay? So right, for a moment, I don't see how you find the intersection, like a point in the intersection of these two planes, but I'll post solutions to this a little bit later. And like it's just some algebra that would take me a few minutes, but since I'm already 4 minutes over, maybe I'll stop while I'm ahead, and you should definitely read the solution to this if you're confused, okay? Okay, so that's all for now. Yeah, so the computation of finding like a point that lies in the intersection of two things can be it can be a little bit annoying. Like basically you just have to pick a y and a z and such that there's an x that works, okay? Yeah, sure. And of course, stay after for a sec if you have any questions, okay? Hi, do you have a question? So as an addendum to this lecture, what you have to do in order to solve these is you take the two equations to the plane and then you can subtract them, okay? So subtracting them gives you this equation here. And then what you can do is you can plug in y is equal to -3 minus 2z, which you get from subtracting these two. You get 0 minus y minus 2z is equal to -3. And then you rearrange this equation to get this, okay? So then when you plug it into these two equations for the planes, you end up with this equation, which through some algebra you can resolve to get this. And then from the other plane, you likewise just plug in this equation for y, and then you get out, you similarly get out this equation, all right? So solving this lets you figure out, oh, sorry, these should be negatives, I think. Solving these gives you that z is equal to +2. It gives you y is equal to -1 and x is equal to 0. So you can go through the algebra yourself. And now we want to check that this point lies on both of the planes. So 2, sorry, -2. So it was a 2. So -2 for the first plane, +0, and y is 1, not -1. So you get -2 +1 +0 +1 +1 gives you 0, so that's good. And then for this one, you get 0 plus 2 minus 6 plus 4 is also equal to 0. So over here. And that gives you that this point actually does lie in the intersection of both planes. And so remember, we had this part of a parametric equation, and all we have to do now is add to this the point 0, 1, minus 2. Okay. Great.